Good morning. Good morning, Josh.
Good morning, Mark.
All right, good deal. I'm glad my audio is working all right.
Yeah, it's always a good start.
I know.
So if you're ready, you can probably just jump into it. A
Yeah,
lot of
sure. I
people
wasn't.
end up watching the recordings rather than attending the live session. So
Okay, sure. All right. Well, let me see here if I can share my screen. Uh, this one. Okay, is that showing up?
yeah, I see your whole desktop.
Yes. Let me see if I can. I'll just blow up this thing for now. Uh, Full screen. What?
That didn't show up.
That wasn't exit okay. That was bizarre. Let me see if this is the first time I've tried to use the Google. What if I say present? Does that do? Oh wow. Okay. Well, I
Yeah,
guess
that's close
is this
enough.
close enough? Yeah.
Yeah,
All right. All right. So I've got this big fancy sounding title here about Ceph daemon autonomy and continual learning and stuff. Well, really what this comes down to is I've got some slides here that I want to go through kind of as we talk about the code. But what it really comes down to is I'm trying to make the OSD smart. I want them to do smart things and not to kind of force on the user a lot of decisions that one they're not necessarily real good at making, and two is kind of irritating to have to do. So I'm going to make a little bit of an assertion here that configuring Ceph kind of to me right now feels like managing a hive, where you as the user are kind of expected to be like the queen bee, telling all of the OSDs and all of the mons and everything else exactly what they are supposed to do. I kind of got this the analogy recently. I've been reading Ender's Game with my kids, and there's a really good quote there that every single one of our ships contains an intelligent human who's thinking on his own, and every one of us are capable of coming up with a brilliant solution to a problem. The kind of enemy bugger fleet, who are kind of like giant insects, they only come up with one brilliant solution at a time. They think fast, but they're not smart all over. And in terms of how Ceph kind of works in so many other ways, we have kind of distributed smarts, right? Um, the whole concept kind of behind Crush is that you're distributing this decision making process. There are rules. There are very strict rules about how it happens. It's all deterministic, but but you don't have the user having to kind of come in and say, okay, this thing went down, so let's place data over here or something. It'd be crazy, right? It'd be way too much work. No one wants to deal with all that. So I think that we should do something. We should think the same way about our options, kind of at a very high abstract level. Um, my thought is that it's much better if users define goals. This is kind of the goal that I'm trying to accomplish with this setting, and I don't want to think about it. I don't want to have to, you know, try to finagle or finesse very fine-grained behavior. I just want it to do the right thing, and here's why I think the right thing is. Um, so right now, we've got, like, I think last time I counted, it was somewhere, I think, between 200 and 300 options. in options.cc, and at least a variety of those, not all of them are documented, and then controllable through Ceph Manager. Probably, I assume there's some GUI that has at least a subset of these, if not all of them, defined that they can set. Just is kind of madness, frankly. So I guess, okay, here's an argument about crush, but we kind of went over that already. My thought here is that, okay, what can we identify as kind of like a good starting use case for thinking about things differently? The one that kind of came up was memory management in the OSD. I actually observed some users struggling with it, especially in the way that the caches in BlueStore are defined and how they affect memory usage. And kind of the thought in their head was, okay, well, I have got these nodes that have this much memory available. How do I set all of this stuff so that my OSD will stay within that and use this memory in an effective fashion? And at the time, this was like 8 months ago, 9 months ago. We didn't have a really good answer. It was kind of like, well, tweak these things and try it out and see where you end up. And it was awful. So this seemed like a really good starting case for this. So the very first thing is that I kind of, well, this isn't exactly true, but one of the early things I started looking at was trying to just say, can we make the OSD fit within a certain memory target? Can we make it so that it's fairly well behaved? Kind of optimally, right? You'd actually pre-allocate all of the memory, and you would stay in it that way, and you'd have a lot of guarantees, or at least you'd be more guaranteed to stay close to that memory range. But we don't have the luxury of doing that right now. It'd be way too much work. So I cheated, and instead, what I kind of started looking at was, okay, well, tcmalloc gives us all this information about the heap memory usage, and some other useful statistics about like what's mapped and what's not mapped and this kind of thing. So we've already got code in place to programmatically grab all of that. So I started thinking, well, okay, I have control over the size of all of these caches, and in fact, we already kind of set a target value for the caches in general in BlueStore. So maybe we can just start adjusting this up and down to kind of react to how much memory the OSD is using. It's a little more complicated than that, but it sort of generally works. So after thinking about this a lot, I came up with kind of a very simplistic algorithm for deciding when the total amount of memory available for caches should increase and when it should decrease. So the idea here is that we have an OSD memory target, how much memory we want the OSD to use. We also know how much memory has been mapped by the process. And that then kind of gives us the ability to find a ratio of mapped memory to target memory. This particular example gives a case where it's lower. So the mapped memory is smaller than the amount of target memory. So we want to increase it. So kind of over time, we take a look at this and we say, okay, where are we at? What's this ratio? Now, based on the minimum cache size that we want and the maximum cache size that we want and what that previous value was, we can take the ratio of memory that's been mapped to the target, and we can use that to increase the memory kind of based on what range we have. So the idea here is that we're kind of slowly growing this memory, and as we get closer to cache max, we end up growing even slower. So we're just really kind of incrementally getting closer and closer to cache max, but that's the limit. We don't want to exceed it. But now, what if, for unknown reasons, other things come in, the amount of mapped memory is greater than the target memory? Well, in that case, we instead look at that ratio, which is basically just kind of what gives you kind of the ratio of overage, and then we remove memory based on that. But instead, now we're looking at the kind of the previous cache size compared to the min. So we bounce away basically, and we bounce away with kind of a greater force than we do when we're approaching it. So as we approach, we get kind of weaker and weaker, right? We don't want to end up kind of aggressively hitting that cache max. We just kind of want to generally get slower and slower, move closer to it more slowly and more slowly. But if we exceed it, if we exceed our target memory, then we kind of want to shoot away from it quickly and just kind of, again, start growing slowly as we approach it. So this is, I'll actually go into the code in a little bit here, but this is basically the algorithm that we just talked about that's implemented there. And it actually took a little bit to get to this. There were a lot of false starts that ended up kind of making some comical looking memory behavior in the OSD, but this works pretty good. So actually, you know what? Let's actually go look at the code now. So where is it? Not what I want. That is what I want. Go. Is that readable, or do I need to zoom in more?
That's readable. It might help if you put it into unified diff mode so it's the whole screen.
Yeah. There we go. Okay. So I could probably make it even just a little bigger. All right. So maybe we'll start out here, just at the options that we're specifying. Of course, we just talked about the OSD memory target. This OSD memory base and OSD memory expected fragmentation, all this is really doing is lowering the maximum cache to be some ratio of the OSD memory target. We're basically saying here, okay, well, we're kind of estimating some base memory usage in the OSD once it's kind of at a steady state. And then we're expecting some level of memory fragmentation. So as the amount of memory that we're requesting changes, as the user changes, that requested amount, the target changes, it just makes that curve look a little bit different. And you can kind of tweak it, but it's not really something that users need to worry about. As we account for more things in this system, right now it doesn't have any knowledge about the RocksDB write-ahead log mem tables, so the buffers that are there. It doesn't know anything about those or anything about like pglog right now. So this 768 megabyte number is just kind of made up to take that kind of stuff into account. But at some point we could actually really factor it in, make it so that it knows about these things, knows how much memory is being used for all of these things. And then this kind of expected fragmentation and memory base number could go away entirely. It would just, kind of have an idea of what other stuff is potentially using memory. okay, so OSD cache min, that is the minimum total amount of cache of memory that should be devoted for BlueStore caches. So if, for example, we have a memory leak somewhere and the autotuner is attempting to like fight it, basically, it won't go below this amount of memory available for cache. So it'll just at that point say, okay, I've set everything to the lowest values. I'm lowest aggregate amount of memory I'm going to assign to this stuff. I give up now. I've done my best. We're done. Or in a scenario where potentially you've set the memory target so low, like say 256 megabytes or something. It can't do much with that. It'll say, okay, I've set the total aggregate cache space down to 128 megabytes. I can't do anything else. The memory usage is going to exceed our target. That's just the way it is. The resize interval here is how many seconds we wait between basically doing this analysis of the cache size and how much memory is being used. You don't want to set that too low. If you make that too small, it will really make tcmalloc kind of thrash around. It's just not. It doesn't really. It's not really worth it. I've played around with it a fair amount, but yeah, it's just not really useful. 1 second is enough, though. That if there's not like some kind of crazy exponential growth somewhere that is a problem in and of itself, that seems to be often enough that we can do a pretty good job typically of kind of keeping things reasonably steady. Not totally perfect, not 100% within guaranteed to be within our target range, but pretty close. All right, so what else we have here? Now this is just changing other levels and things, nothing interesting. All right, the CMake list change, that's also not particularly interesting. All right, here in BlueStore.cc, we're adding in perfglue heap profiler that we can make our calls in to find out what we're using. This is all just nothing interesting, really. This is just getting all of our stuff into the place where we're going to look at the options and things. Right. In trim shards, we are now making it so that we are looking at potentially the auto-tuned amount of memory versus the kind of static one that's defined in the ceph.conf file or wherever. The idea here is that we want to still allow a user to set this stuff themselves if they want to. It's the kind of idea, right, is that it does things automatically by default, but if the user wants to override it, then they get very we don't do anything automatically at all at that point. They get control, they do it. So this is all stuff to support that, basically. Okay. Okay, this is just more of the same. Nothing interesting there. Here we go. Now we're getting into the meat of it. So, tune cache size. We're grabbing all of these options. Basically, these things are being read in the BlueStore code, but then we've got this mempool thread now where we're actually just asking to grab them from BlueStore. So BlueStore is a thing that hopefully registers listeners for all of this stuff and sets up right, and then we just grab it every time here. So we talked a little bit about fragmentation and the cache max values. Up here, you can see that's exactly what we're doing. We're basically just restricting our cache max based on the amount of fragmentation we expect and the base memory value. We grab, here we go. We're grabbing the different heap statistics that we're interested in. We also, beforehand, every time we're iterating through this, we're releasing the free memory. There is a way you can do this through the admin socket, but people don't. I don't really think people use it. I would much rather use it here on kind of the same schedule that we're doing everything else. And I mean, we're not doing that often, really. So this helps us keep everything kind of well controlled. So okay, then we are grabbing the heap size and the number of unmapped bytes, and then we compute the number of mapped bytes from that. That is not the amount of RSS memory that is used by the process. Unfortunately, we can't force the kernel to reclaim that. It does it on its own as often as it feels like. On Ubuntu, we saw it kind of in low memory pressure environments, not reclaiming memory to the point where the amount of mapped memory differed from RSS by like 20%. But on CentOS, on our CentOS machines, it was very, very close. And I suspect on the Ubuntu machine, it would probably, the kernel would be more aggressive about reclaiming the unmapped memory if there was a lot of memory pressure. So I think it's probably okay, but the kind of the irritating thing is that when users look at the amount of RSS memory by the process, they will see that it's maybe higher than what they set the target to be, even though the mapped memory is very, very similar. So it's kind of unfortunate, but it is what it is. I'll show some graphs later on. Okay, so we're defining a new size, and we're first setting it to the old size, the autotune cache size. And then we're basically just bounding it by the cache min and cache max. So if things have changed, if some of these settings have changed, in between iterations, this basically just sets everything so that we're within our boundaries nicely. Okay, and now this is the code that we were talking about earlier. This is all it is right here. Basically, if we're under the cache max, we are going, or sorry, if we're under the target value, if the amount of mapped memory is under the target value, then we're going to adjust our size so that it kind of slowly approaches cache max. But on the other hand, if the amount of mapped memory has exceeded whatever the target is at this point, then we're going to more aggressively reduce the target size so that now, hopefully in the future, the amount of mapped memory has shrunk, and we'll kind of end up back in the stage where we're slowly growing back up to the target. And really, that's it. There's some other stuff here for dumping stats out and everything. It's really surprisingly simple. There's not a whole lot going on. Yeah, this is just setting these things. It's not interesting. So, okay, Josh, how much time do I have? Do I need to be done soon, or do we have more time?
We can go for another half hour if you like.
Oh, fantastic. Okay, so then I will keep talking. So that is the PR that introduced the memory kind of auto tuning, but we did more than that. kind of the simultaneously while this was going on, I was trying to think about, well, okay, that's great that we've now got kind of the overall target for the memory usage of the OSD. People don't have to think about that much anymore. But we still have this issue where no one has any idea what any of the BlueStore caches should be set to. It's super confusing. It's confusing even for me sometimes. And that has to do with just kind of how our caches used to work and how the RocksDB block cache works, because it's not intuitive unless you actually read the code. There are things that they have kind of this concept of high priority and low priority cache just in their LRU cache, not in the clock cache. And what's in the high priority cache and what's not in the high priority cache isn't super well documented, and there's a lot of options that govern it. So anyway, I was thinking about all of this and trying to think about, okay, well, maybe we can make this automatic, because there's no real good default for these things anyway. If you have an RGW workload, you might want a lot of ONodes to stay, or sorry, OMAP entries to stay in cache. But if you're doing RBD on BlueStore, you might want a bunch of ONodes to have really, really high priority in cache. But ONodes can also be cached in the RocksDB block cache. It's hierarchical. And theoretically, they might be a little smaller because we're doing variant encoding. But then that encoding means that there's more CPU overhead to do the encode and decode. There's tons and tons and tons of variables, and it's impossible for anyone to really figure this out. So what I want to start looking at is, can we make it automatic? Can we kind of use the same idea where we're periodically looking at different statistics and then adjusting the ratio of that memory target memory amount that we set in this previous PR, and then split that up in a smart way between all the different caches. The first attempt at this was basically just to implement a very high level interface for our caches that basically started specifying priorities and byte values for priorities. The idea here is basically you've got some kind of controlling thread that's periodically going through and asking each cache for each priority, how much memory would you like for this particular priority? And then this kind of controller at each priority asks these questions, and then based on how much memory is available and kind of a fair share ratio for each cache based on kind of the initial ratios that are set in the ceph.conf file, says, okay, you get memory, you get memory, you get memory, kind of based on these things. You've asked for more than your fair share ratio, so I'm going to kind of keep you in mind, but here's how much you're going to get right now, and because you've requested a lot. Or another cache has said, I don't care, I don't have anything, I don't need any memory. Okay, here, let me just give you the small amount you want, or nothing if you don't want anything at all. Although it will get something because we give each one a little bit of headroom. And then at kind of the end of this round of at a given priority, then we say, all right, who still wanted memory? Which caches still wanted memory, even though they already got their fair share? Okay, so let's go through now and then start dividing up the remaining memory and see if now we've satisfied the requests. And we keep doing that at the given priority level until every cache is satisfied, or we've run out of memory, one of the two. Let's say every cache is satisfied. Great. Okay, now we've still got some memory left. So let's move on and repeat this process at the next priority level. So, the highest priority things are first getting memory assigned based on their fair share, but eventually we keep iterating through, and they hopefully get as much memory as they requested for that priority level, for a very high priority level. And then we maybe go down to a medium priority level or a low priority level, and just kind of repeat this process. So no low priority items will get fulfilled unless there's memory available. because we'll give everything what it wants at higher priorities first. All right. And weird. Okay. Um, so kind of a first pass at this was looking at the RocksDB block cache. They already have kind of this concept of high priority items, specifically the Bloom filters and the indexes for the SST files are really high priority. You really want those to stay in cache, because if even if like an item is not in cache, by having that Bloom filter in cache, you can avoid a lot of reads as you iterate through all the levels of RocksDB. If you don't have Bloom filters, potentially you could look for something in every single level, have to do reads in every single level to find where exactly in RocksDB it is. But if you have those Bloom filters in cache, and if you have a reasonably high number of bits devoted to them, you can say with fairly high certainty, or you can avoid, I guess, situations where you have something that wasn't there, but you have to look anyway, right? So you can avoid a lot of the reads, basically. So those things are really important. Indexes, filters, they also include recent reads. I didn't actually like that. That was one of the things I didn't want there, because I kind of want more control over what things go into the high priority cache pool that they've defined. And I want to adjust that cache pool. I want to change the size of it. They don't really typically do that in RocksDB. The capability is there, but they haven't exposed it as part of their public interface for the cache. So our first kind of attempt at this was to change the cache interface to expose all of this, and it worked. That's how it kind of first worked. We submitted PRs to the RocksDB guys, and they sat there for like 2 months. They were super nice. They were encouraging about all of this, but they're kind of like, well, we really don't want to modify the interface, and it's totally understandable, right? Because that's a nice static interface that they've had for a long time. And here we are coming in with this weird custom stuff that most likely we will be the only ones that will ever use. So the end result of this, kind of in this first pass, was that we still had it. We still had kind of our own modified version of RocksDB with our own modified public interface, and we used their cache, their LRU cache, and inside our implementation, this is actually in the RocksDB store, the key value store. We implemented the priority cache interface. It's kind of a weird thing to implement it here, but that's what we did initially. And here you can see we are fulfilling the priority cache requests. So this is when this kind of the BlueStore mempool thread is the thing that's kind of acting as the overall controller for all of this. And it goes in and it requests from the caches, how much memory do you want at a given priority? And here, this is exactly what we're doing. We're saying, okay, let's look at what the high pri pool usage is for priority 0. That's the highest priority here. And then we're going to chunk it. So we'll basically push it out to some larger boundary so that we give ourselves some headroom for growth. And then we also potentially have some already assigned memory here. So we're only going to request more if it's, kind of not, if it's, greater than this. And then we've got this last priority here. And those are the only 2 priorities we're implementing first. And that's for everything else, basically. The rest of the usage, not just the high priority pool usage. So everything else basically gets shoved into the last priority. There are interfaces like this for the other caches as well, for the BlueStore onode cache and the BlueStore buffer cache, but they don't really do anything yet. All they're doing here is basically sitting at the last priority, just like the RocksDB block cache. The only thing that we're really prioritizing with this and kind of the prototype implementation here is making sure that the indexes and filters are always being cached. The one thing that it does do, though, is that whole process that I talked about, where we're kind of iterating through the different priority levels and asking things what they want and assigning things, and then kind of divvying things up based on the ratio. If something doesn't request memory, if like the buffer cache isn't requesting memory, then it's still the case that the onode cache might get more of it. We had some kind of weird behavior like that already in BlueStore, but it didn't work quite right. It actually had some bugs in it, and the ratios didn't really look the way that they were supposed to in previous versions of Ceph. So we almost had this kind of situation before where we told the user, you need to figure out what these ratios are, but then we kind of almost overrode those and sort of used them, but sort of made our own decisions. It was kind of like you had worker bees, but the worker bees were insubordinate and not doing what they were told. So the end result of all of this stuff is that if you look on the right here, that's kind of the auto-tuning disabled behavior. And actually the correct auto-tuning disabled behavior, not kind of the weird kind of hybrid behavior we had before, where we've specified specific cache ratios for the different caches, and we're not using the memory auto-tuning that we implemented, that we talked about earlier on. So the RSS memory, or sorry, the RSS memory usage for the process is quite high. A kind of static 3 gigabyte BlueStore cache size has been set, and then all of these different things are kind of using, they're up to their ratios here, right? If you figure out what the 40% of 3 gigabytes is, or 20% of 3 gigabytes is, they're sticking to them. In our auto-tuned case, though, now we've specified that we want a 4 gigabyte OSD memory target. So they're sort of comparable, right? You think, well, okay, if I do a 3 gigabyte BlueStore cache size, maybe that makes my OSD process around 4 gigabytes when you count the other overhead and things. But in this case now, we've just set the target, and it's figuring out what the cache size should be. So now instead, it starts out like around 2.7. That's based on our OSD memory base and fragmentation values. That kind of starts out there. But then it turns out that that's too much. We've kind of gone above, and so now we're dropping the amount of cached memory down and kind of adjusting it below 2.7 gigabytes there. It's maybe more around 2.5 or 2.4 or something, kind of variable. You'll see that the mapped memory in the light blue is very, very good. It's very, very close to around 4 gigabytes. It sometimes spikes over a little bit, but it's staying really close. The RSS memory usage is higher. This was our Ubuntu node where the kernel was not aggressively reclaiming unmapped memory. And so the RSS memory usage of the process ended up being higher. I suspect that if we had memory pressure, that the kernel would be more aggressive about reclaiming that. So those would probably be closer. On CentOS, we see them much closer, at least in our test lab. The CentOS kernel settings appear to be far more aggressive about reclaiming unmapped memory, even when there isn't a significant amount of memory pressure. You can also see here that very initially, the amount of memory allocated for buffers grows really quickly. That's that little green line. It spikes up because when we're doing writes like this, initially you end up with a lot of buffers that potentially you could cache. And that's getting the majority of the memory at first when we're going through that iteration process that I described. But as time goes on, we see that O-nodes, the amount of O-nodes that have been written increases dramatically. And so that's starting to get a higher proportion of the cache. And over time, this is an RGW workload, the amount of OMAP data starts increasing, and those indexes and filters get bigger. And so we start seeing that there's some value in caching that. And at the same time, the amount of buffered, the amount of things in the buffer cache, the amount of data in the buffer cache, and the amount of data in the O-node cache ends up decreasing over time. But it ends up recovering when we have these spikes. These spikes, I think, are maybe when RocksDB is doing compaction and it is storing the SST files in the block cache. And so all of a sudden there's this huge request for more memory. And this is the auto-tuner basically, or this whole thing, this cache priority system responding to that, saying, oh, hey, look, all of a sudden we've got this more data coming in, probably both at the high priority level, which is this kind of continual growth, and then at the lower priority level, which is the spike here. But because we've said that we want 40%, up to 40%, a target of 40% of the meta cache, sorry, the KV cache, because that we've set it that high, then it gets in the first round a higher percentage of the memory, and these drop down. But then potentially as those SST files end up being evicted from RocksDB's cache, then it doesn't need as much. It says, I don't request nearly as much. I don't want it. I don't care. Then the buffer cache and the meta cache end up getting more of it. That was an RGW case. This is kind of similar here for RBD. In this case, you see that the amount of data in the key value store for RocksDB is much lower. This is kind of a simplistic view of it, because in this case we had enough memory that we were able to fit all of the BlueStore O-nodes in cache. This, you can kind of see here that it stabilizes right around 1 gigabyte, and then there's plenty of memory for additional meta cache and for everything basically. It turns out that the data cache ends up basically just getting I'm sorry, I got those backwards. The O-node cache ends up is the yellow line that gets the steady state. It grows to a point and then it stops. And the data cache is basically getting whatever's kind of left over here. We've set to 0.2. It's getting more than 0.2, but it's basically the leftovers in it over 0.2. It's the leftovers that the KV cache and the data cache the meta cache did not want. So that's why it spikes up again here at the beginning, but then it shrinks as the KV cache and especially the O-node meta cache want more. And you contrast that with auto-tuning disabled, and there you've got close to 5 gigabytes of OSD memory usage because we're not tuning that at all. But the amount of cache that's devoted to these other things is just static, whether or not it's useful. So that's kind of the overview of how it works. I guess we don't have too much time left here, but I can quick pull up this. So here's the request cache bytes interface. The implementation in the RocksDB. store. So that was what we were looking at earlier. But that's not what I want to show you guys. I want to show is here. So there's just some random cleanup stuff and some changes to trim shards and that thing. The really kind of interesting thing is this. This is the process by which we're iterating through the different priorities and the different caches. So we start out with this kind of global, well, not global, but this mem avail, and then we go through and ask. Well, we go through for each priority is kind of what we're doing here, and running this balanced cache priority method. And eventually, after we've gone through all the priorities, if there's any left after all of that, then we just kind of equally, well, we divide it based on the ratios that have been set. So just if nothing wants cache, then that just ensures that everything gets some share of the memory. But then balance cache pry, this is where at a given priority level, we've passed in the amount of memory that's available, and now we are iterating through, looping through, and doing that process that I described earlier. We're asking each thing what it wants, and then we're looking at kind of the ratios that that we can that's kind of like the fair share, right, of what it theoretically should get at this level. And then if it wants more than kind of its fair share, we give it what it wants, but we keep it in mind and go through and kind of do this for everything, right? So each thing is just getting up to its fair share to start out with. And if that satisfies it, then we remove it. Otherwise, we keep it around. And we go back through and do this process again with whatever memories available until all of them have been removed, or until it's run out of memory. So that's kind of it. That's how this works right now. This is more or less what's in master. There's one other commit in master that that basically goes through and then I had mentioned that the RocksDB guys didn't like this, where we're changing the interface for the cache. So what we did instead is we switched back to master, and we took the RocksDB LRU cache code and implemented it in Ceph itself. We basically took it, imported it, and then now we can use the interface the same way. RocksDB gets our cache through the public interface, but now we can go in and poke at it ourselves. We can look at what is happening in the high priority cache. We can change what's happening in the high priority cache. We actually here this is something that changes the whether or not recent read hits are promoted into the high priority cache, and that's not actually useful for us right now. We don't want that, specifically because what's coming in the future in another PR is that we have a system of not just two priorities, not just low and high, but an arbitrary number of priorities, where by default it's set to be 10, but we can stratify all of this, and we can make decisions about whether or not something that's at priority level 1 in the O-node cache is more important than something that's at priority level 2 in the other cache. And we do this through kind of a system of age bins that get added to all of the different caches. We don't have time to talk about it here, and the code's not actually in master. It's in another PR that unfortunately failed QA due to a seg fault. But it mostly works, actually, when it doesn't seg fault, I guess. And it's really neat because then you can kind of have the OSD dynamically reacting to the kind of the kind of IO that's happening. Maybe O nodes are more important. Maybe OMAP is more important. Maybe there's some trade-off between these things. You maybe still always want the KV cache to absolutely get the indexes and filters cached. So that's always high priority. But then other things can kind of shift around. It's really neat to see it work. There is one problem though with all of this is that when you get aggressive about doing this, it really makes TC Malloc kind of unhappy. It wants to like shove like-sized things into bins so that it can make like good allocations with them. And all of a sudden here now we're like moving. We're saying this set of things is getting more memory, and now we're changing it over here and doing things. This has to be kind of a slow process. We can't do it quickly. I think it's 1 second for changing the amount of memory that's available in general, and 5 seconds for this process of like kind of renegotiating how much memory should be devoted to each individual cache. So let me just check and see if there's anything else here I want to go over. Okay, yeah, so we talked about this where we pulled in the RocksDB cache ourselves. One other thing that's nice about this is that now we can kind of Cephify it. We can make memory allocations for that cache be part of the mempools so that we're tracking how much memory is allocated to that cache. Not just in terms of like this priority system, but in terms of allocations, and maybe someday making slab allocations or something else for it. And reusing common data structures. They've got RocksDB kind of had their own custom small vector like implementation, and we can just standardize on this now and use it in multiple places depending on if we want theirs or actually small vector itself or whatever. Also, they did some kind of shady things with memory allocations where if you've ever heard of the struct hack in C, it lets you basically do a malloc and then for a larger amount of space than a struct takes, but then at the end of your struct you have like an array that you walk off the end of, but you can do it because you've got malloc space for it. And it's really evil, but there's actually a legal way you can do this in C, but not in C++. And so they're doing it the illegal way in C++, basically. It works with GCC. It works definitely. With other compilers, it might work, but it's definitely not valid C++. So we changed that. It might be a little slower, but it's definitely nicer to work with now. And it was necessary to be able to do the things that we're doing, where we're modifying the caches in the future for doing this age binning. Yeah, I think that's basically it. Oh, also there's some other things that are coming. Automatic chunk sizing for doing the chunky allocations. That just basically means that the more memory you have, the bigger chunk sizes it makes, so that you're kind of not just allocating tiny little chunks if you've got tons of memory available. And then also there's where this new PR is moving the cache balancing code out of BlueStore into this kind of generic priority cache manager class. I would really like to, even if it's not that useful, I'd really like to make this OSD wide for FileStore and BlueStore, and maybe potentially do something like this using this priority cache manager in like the Mon and other things, so that users get away from this idea of setting, okay, I'm going to have a 512 megabyte cache for RocksDB in the Mon. Well, no, let's not do that. They don't know how much they should assign. Instead, maybe we just say, okay, the Mon should use 4 gigs of memory or 2 gigs of memory or whatever, and then we just handle it behind the scenes. And then the user knows, okay, this is the envelope the Mon's going to try to fit into. the cache gets adjusted based on what other stuff is happening, and then we just kind of go from there. I think kind of making it all universal and very straightforward for the user is kind of the end goal of all of this. And if this all works, if this works really well, then maybe we can start thinking about things like doing similar stuff for disks. It's more complicated for sure, and the act of migrating data around is definitely very impactful. But I'd love it if we just handed OSDs or handed daemons in general a chunk of hardware, memory, disks, whatever, maybe cores to operate on, and said, you figure it out. The user doesn't need to be involved. Just figure out how to best use these resources and use your own internal statistics to do it. So that's it. That's everything. Any questions?
Okay, curious about, you mentioned the automatic chunk sizing in the future. What kind of impact do you see that having?
Well, I think it's kind of a small thing. It really, all the chunk sizing is doing is basically making it so that when memory is kind of divvied up between the different caches, it's chunking it, right? So that in the future, like you might not need to grow it if it's growing kind of slowly. It just stays the same. So kind of the whole point of that, right, is to make it so that we're not changing the ratios. So maybe tcmalloc doesn't have much more work to do. I mean, all it really does is say how much you evict, right? When you're going through and doing cache eviction, now you've got maybe less stuff that you need to evict, right? Because you've got a little bit of headroom, so you don't do it until you hit that. With the automatic chunk sizing, all it really does is says, okay, if you've got lots of memory, give it more headroom, is kind of what it comes down to. Or if you've got like nothing, there's no memory available, then make a really small chunk size so that we can like fit as much into our space as possible. So I guess, it's small memory values, then you're not going to have quite as much waste as having a static chunk size. And at large values, it makes it so that, well, you've got a lot more headroom, so eviction doesn't start happening. Maybe you stay ahead of eviction if you've got room for growth, and you only start really evicting once you've kind of gotten to the point where you're so saturated with everything that you have to. I don't know. It's kind of neat. It's useful, but I don't know that it necessarily makes a huge difference in the long run. Maybe it does. I don't know.
Okay.
Does that kind of make sense?
Yeah. Thanks.
Any other questions?
Hey, Mark. So would you be making these slides available as part of your video?
Yeah, sure. That's totally fine. I literally stopped working on them like 5 minutes before this presentation. So they've never been put anywhere or anything, but yeah. And what I'd like to do too is once I get the next PR working, right, and get that into master, I think it'd be good to do another one of these, because the next piece is the really cool piece where we're actually modifying the caches to do this age binning. It's kind of what makes everything really work. The stuff that's in master right now, more or less works, but it's really simplistic. There's basically just there are two priority levels more or less, and one of them is only used for RocksDB filters and indexes and filters, and the rest of it's basically just all at the last priority level. But with that, then we start actually looking at kind of how old is the stuff in this cache, how old is the stuff in this other cache, and how should we do that based on the age curve, the bins, the overall bins. So I'll have more to talk about then.
Thanks, Mark.
Cool.
So just to give you some more context, I am a total beginner at Ceph, so I'm just getting to with Ceph. So I didn't quite follow a lot of things that you talked about this in this video. Just to get some more context when I revisit this video in the future, as a beginner, what are some things that you would recommend that I start looking into? Would it be RocksDB to begin with, or BlueStore, or anything else?
Well, sorry. What are you kind of trying to do, or what are you interested in?
I'm just trying to understand Ceph, on a big picture level. So,
Okay.
just trying to play around with Ceph.
Sure.
Really have any idea what I would get into in detail.
Yeah, this stuff is all amazing, right? This is like, digging into the guts of how XDB works and how kind of BlueStore is working. I would look at how Crush works and how kind of the overall kind of design behind the monitors and the OSDs work. Probably I don't know, Josh, do you think Sage's paper would still be useful to read?
Yeah, if you want that level of detail, Sage's paper is still pretty relevant.
Yeah.
If you're just looking for a higher level picture, there's plenty of intro talks on YouTube that go over the architecture at the higher level. That might be a good place to start.
Cool. Thanks, guys.
Sure.
Cool. All right. Well, I have a meeting I have to run to, so have a good one, guys. It was fun.
All right. Thanks, Mark. That was fantastic.
See you later.